2 more lecture. But yeah, so today I will continue Heisenberg spin chain. So spatial one dimension. This is Heisenberg XXX spin chain, and we will solve this system exactly. So this is the so Hamiltonian is given by this one-dimensional Hamiltonian. So Hamiltonian is given by the essential power matrix S plus minus whatever xn xi is equal to power matrix over 2, essentially just normalized, and then you have a Hamiltonian, and then so ground states. So ground state is all spin up or down, and then so ground state is the essentially all spin up. So we are solving the scattering amplitude for n particle. So this is ground state. And of course, this corresponds to the all the so energy can be easily determined by the interaction is super easy to determine since it's all spin up. So you have a 1/4 from the just next spin each other, and then you have a we impose a periodicity condition enter the L side. So that's why we just write down the Z over L over Z. And we want to determine the system. So we want to find the spectrum. So our goal is to find the energy and momentum. And also, more important is scattering matrix, S matrix, exactly in this model. So that's the goal. And to do that, so first we consider last time we consider one Magnum state which has plus, and at some point you have a minus sign. And then plus, and we call it so the position is n. We call it n, and we consider some linear combination of the state is some linear combination of e to the I k n and n. So this is coherent state. N is the T over LZ. This is coherent state. So that's what we consider, and we derive. So this is, it's super easy how this Hamiltonian acts on these coherent states to determine coherent states. So this is called, and we determine the ek minus e0 is equal to j 1 minus cos k. Cos k. So this is the eigenvalue. So it's straightforward exercise to do that, to using whatever sum of Sn plus S minus n plus 1 acts on this n. I think I should call m maybe, and which is equal to n plus 1. And then if you swap the minus and plus, sorry, n plus, and this becomes n minus 1 sum, and then so it's just eigenvalue. is equal to L minus 4 over 4 M and psi. So we just swap adjacent spin by just quarter to one minus 1/4. So and you have two adjacent spin which has a different spin, one and so from here you get the 1/2 energy difference, and from this place you get the 1/2 difference. In total you have a 1/2 plus 1, and then so you have minus 1. So that's the difference you will get, and then you can just act this Hamiltonian on this coherent states. We saw this one. We saw the energy difference is the 1 minus cos k. So therefore, this will give you gapless states. I mean, the system is gapless. So that's the one magnum coherent states, and then so we consider two magnum, which is plus and plus, whatever, minus and then plus, plus and then minus and then plus. So we just swap the two spin to down. So and then we call this position N1 and 2. N2, and we call it N1 and then N2. Okay. So that's the and then we consider this. We want to consider the eigenstates of this Hamiltonian with the two spin are going on, moving down. So that's we are considering, and then so separate 1931. So Bede assume, so the in the ansatz, Bede ansatz means assumption. Since this magnum or like a spin down states behave like a really plane wave particle, so that he made an assumption that the wave function takes the following form. The following form. So it's a plane wave, and if you swap the two states, you have a different B, and the difference between A and B is called scattering amplitude S matrix. So I forgot which one is notation. My notation A over to B. Yeah. So A over B is essentially scattering matrix S matrix. This is the S matrix. In other words, so you have the one magnum and another magnum. You have a S matrix. You have a K1 and K2, and a K1 and K2 is given by here. But here you have N1, N2, and N1 and N2. So you have a scattering, and we want to determine this S matrix exactly by using this coordinate beta ansatz. So that's the our goal. So this S is different from that S, so you understand what I mean. And so last time, so we applied this Hamiltonian on this two magnum states coherent. Yeah, this coherent coordinate beta ansatz equation. I'm sorry, coordinate beta ansatz wave function. And what we have found is that the two set of solution. Yeah. So what we have found is that the E minus, so the system E0, sorry, Hamiltonian acts on, maybe I should write down Hamiltonian. Hamiltonian acts on psi is equal to E minus E0. Remember E0 is over there, and psi. And then what we have found is that just by just acting on this Hamiltonian here. So last time we did the explicit computation, and Yeah, video is already there, so you can watch the video derivation. I'm not going to repeat again. And j2 minus cos k1 minus cos k2. And then cos k2. So, and what we have done upside. So if you assume this coordinate beta that's you can just find the state is really eigenfunction or eigenfunction of this Hamiltonian. And then moreover, so what's nice is that you can have just these two magnum states is indeed you have a just linear combination of this one magnum. The energy is just a, so if you call this one is equal to E1k, so this is equal to E1k1 plus E1k2. So this is the what you intuitively you can just justify this is correct. And moreover, one can determine the scattering amplitude if you yes. So scattering amplitude, I think. So last time, so if you plug that one into here, what we have found is in the A over F. So if you write down the sum of F and 1 and 2, and 1 and 2, and then so sum n1 and n2 are this LZ, and the F n1 and 2 is really given here. So if you use this, I think I should call this one is F n1 and 2. I think I should call this one is F n1 and 2. F n1 and 2. And then coherent states is this one. Sorry. So this is correct notation. Okay. So this coherent state is just the linear combination of this plane wave. So this is 1931. Beta has assumed to derive the Hamiltonian energy and the momentum scattering amplitude exactly. So this is we call it exactly solvable model. So then what we have found is that this Fn1 and 2 should satisfy the following combination. Minus, by acting on just Hamiltonian, equal to 0. So that's what we have found last time. So this wave function should obey this condition. That's what we have derived last time. And then we stop by at the end of lecture. And now we can just plug this beta coordinate beta that's into this what we have derived. Then we just plug that into here, and then we can have a plus b is e to the I k1 plus k2 and then plus a plus b and e to the so this part is I k1 plus k2, so I missed 2 here, and plus 1, and then minus 2 I times k1 n plus k2 n plus 1, so just n plus 1, and then b you just swap k1 and k2, e to the I k2 n plus k1 n plus 1. And is equal to 0. So that's what we and if you solve this equation, what we have found is A over B, which is S matrix of this S matrix over there is indeed equal to minus e to the I k1 plus k2, and then plus 1 minus 2 I k1 divided by e to the I k1 plus k2 plus 1 minus 2. Sorry, I missed 2 here. 2 e to the I k2. So this is the model scattering amplitude exactly derived. If you assume this wave function. And then we want to derive so we can, if you introduce the following coordinate lambda I is equal to 1 over tangent of ki over 2. If you introduce this one, so this one can be written as minus lambda 1 minus lambda 2 plus 2I divided by lambda 1 minus lambda 2 minus 2I. That's we can write down I think I made a mistake for sign. So I think I made a mistake in sign. Yeah. So minus. Okay. So that's we can derive it from the. Yeah. So we can just derive like this way. Okay, and we want to generalize this one into the n magnons. So our goal is, so this is 2 magnon, and our goal is to generalize this one to n magnon. So or n magnon. So what we so again, so you have whatever plus, and also plus, but anyway minus and plus, plus and minus. So you n of them minus, so spin down. There are n sides and spin down this way, and we call again n1, n2, and nm. So we call this one is n2, nm. And then again, we can just assume the wave function has the following form. The sum of f and 1 and 2 and m and 1 and m, and then all and I is in the spin L. Okay. And then again, we can use the coordinate beta ansatz equation, coordinate beta ansatz. So instead of just coordinate beta ansatz is in this f and 1 and m can be written as the sum of whatever a q1 qm e to the I k1 kq1 and x1 plus kq2 x2 plus plus k qm xm. Okay. And the q is the permutation symmetry Sm. Okay, you just swap the momentum of the particle q1. So as you can see, so it's just a S2 is just a Z2 symmetry. K1 and K2 is swapped. But now we have the m of them, so you have 1, 2, 3, 4, m, and you can just permute the indices q1, q2, q3, and q4, qm. So permutation symmetry. So if you swap only 1 or 2, you have a 2, 1, 3, 4, and you have to sum over everything. So if you do this coordinate beta analysis. So what we have is indeed, we can just have the, so you have, so 1, 2, 3, And then you have a J's particle, you call it I's particle or J's particle here. And then, so we have a periodic boundary condition, So you have n of them, L of them, sorry, to the up to L. And then, so you just scatter the particle like this way in the coordinate boundary. Okay. So this is time direction, and this is spatial direction, x. And then if you bring this J's particle in the, how to say, bring the J's particle circle around, okay? Makes a circle around. And each time you can have the S matrix here. So scattering amplitude here, S. So this is S J minus 1J. And this is S 3J, and S 2J, and S 1J. And then here you have the periodic bounding condition, so you have a SLJ and so on. Okay. So each scattering amplitude, you have this amplitude scattering. Okay. And since we just bring the J's particle to the, you just, wave function should get the phase e to the kjl if you move the J's particle to the distance L direction. So this is the wave function you should get, the phase you should get, because it's just a translation by kj momentum by length L. And then you just have this amplitude is given by product of j, I is not equal to j, Sij. Okay, so that's what you would expect. So this amplitude should be the product of this scattering amplitude. And if you solve this, so this one, we already derived this one, so we just plug that into here. What you get is a product of I is not equal to j, sorry. I is not equal to j, means the j can be interact with other particle. So I is not equal to j, and then Lj minus Li plus 2I, Lj minus Li minus 2I. So this is the amplitude we will get, the product. And in particular, so if you use this relation, the e to the I kjl can be written as lambda j plus I minus lambda j minus I. So e to the ik. So from here e to the I kj can be written as Lj plus I minus Lj minus I. Okay, and you have a power to the L. So therefore, this one is to the L. So this is called celebrated Bethe-Ansatz equation of Bethe-Ansatz equation of Heisenberg XX extension. So this is a famous equation, and we want to solve this equation to derive the energy and the momentum. Energy and momentum. Energy and momentum. And also remember that the I already forgot there must be the equation. So first we want to take a log of the where was it? I already forgot what kind of equation. Oh yeah. So recall that T1 minus 1 plus 1 minus I x 1 plus ix is equal to exponential minus 2I times tangent inverse of x. Okay, so if you use this relation, one can just take the log of the left-hand side and right-hand side, and then one can derive that the so if you take a log on both sides, you get 2L tangent inverse of lambda j, and is equal to 2 pi j plus 2 times I is not equal to j, and then tangent inverse lambda j minus lambda I divided by 2. So that's what you get, taking log of the above equation. So beta Unbox equation over there, you get this one. And then here ij is again, so what we have learned of the delta function. So this is a beta quantum number. So ij has to be the integer. Do you remember integer? If it is m is odd, if m is odd, ij has to be half integer, a strictly half integer. If m is even. So that's exactly the same as what we have learned in when the Hamiltonian is the delta function. We just learned the time as a time model for scattering matrix to see sum of delta xi minus xj is not equal to j. So this is what we have learned from this. So the time model with delta function, we already know this. So beta quantum number should be the integer when the m is equal to odd, and then half integer. Because this minus sign, you have to keep track of this minus sign. That's what we have done. So if you're really honest person and a very careful computation, you can derive by yourself. Okay. So as we recall, so this energy is indeed, we can just have the, seems like I already erased, sum of E1 with E1. So one magnum energy is 1 minus cos k, right? So that's what we have learned. And the ki. I runs for 1 to n. So it should be, that's what you expect from the two magnum scattering amplitude. So and then the plug that into here, and then essentially what E minus E0. E minus E0 should be this one. And we know the E naught is equal to minus J, and then sum of J equal to 1 to n, 1 minus cos kj minus L over 4. So we already know E naught is J times L over 4, and then you have the energy for 1 magnum. And then we can just use the relation between Ki and then, did I erase? Oh my goodness, I erased. So Ki and tangent, so you can just write down. So I already erased it, but the lambda j is equal to 1 over tangent of Kj over 2. If you use this relation, one can just write down. This one is equal to minus 2j sum of j equals 1 and 1 over lambda j squared plus 1 plus j over 4. Any question?
I'm confused.
Okay.
The Hamiltonian in the up and why we write it in the x. So we write a Hamiltonian before as the spin. So how it converts to x?
No. So this Hamiltonian is very different from this Heisenberg spin chain. So this is very different. So that what we are solving h is equal to j sum of s n plus 1. So this is what we are solving now.
Okay.
But this one is the previous problem.
Okay.
Previous problem.
Fine.
But we also use the Unbox equation to derive the scatter matrix exactly. Do you remember?
Yeah. I misunderstood.
Okay.
I think this could be converted to this problem. So
No. So this problem is very easy to solve. Okay, so to give us some intuition. And at that time, so we already encountered this beta quantum number, right? Beta quantum number. To use this one. And then we can have exactly the same phenomenon in this Heisenberg spin chain. Okay, and then so if you use the translate momentum k to this lambda, one can just write down the energy in terms of lambda. And also here the momentum p is equal to sum of j equal to 1 to m kj is equal to 2 times sum of j equal to 1 m. And then so we just use relation over there. And then so what we have is the minus tangent inverse lambda j plus pi over 2. So that's what we have from just translate k to lambda, and you get this. Okay, and then so if you use this relation, one can just write down. So if you use this relation, one can just write down this one is minus 1 over j is equal to 1 to the m 2 pi ij over L plus n times pi. Okay, so this is how you get the momentum and energy. So this is the momentum energy. So everything can be written in terms of this beta quantum number. So to get this energy exactly, one has to solve this beta Unbox equation. Okay, do you understand? To get the lambda exactly, one has to solve this algebraic equation. Okay, to get the energy and the momentum. Okay. Any questions so far? Yes. Yeah.
Why this equation called beta answer? Where is the assumption?
Assumption is the f. So this one. Assumption is this one. The state is actually. Assumption is state is a linear combination of plane wave. So here, so you have the plus and the minus sign here, and this minus sign has the, so you have the almost up sign, but you have a minus sign, and you have this one has the momentum ki, and this ki is really plane wave. And then linear, and you have the some amplitude. And the ratio of amplitude will give you S matrix. So this is the coordinate beta Unbox. Coordinate. So this is the assumption. And if you assume this one can derive the S matrix here, S matrix here, and also energy and momentum exactly.
As you do have the picture that the S matrix is means any two particles crash into each other and
Yeah.
and this is a chain. How
Yes.
cut two chain? Oh,
So you have a spin down states and a spin down state somewhere. Let's go K1, and this is K2, and everything is up. Whatever. So there's the L side is Z over LC, L side, and the K1 and K2 just go to next to each other, and then there's the interaction by Hamiltonian I over there, and then you can just since repulsible, since spin down states are repulsible, so you just scatter together, and then we were going to take the limit that this L goes to infinity from now. So in the 1 over, so essentially this distance can be understand the 1 over L indeed. And then we take L goes to infinity limit so that the really distance becomes, this discrete model becomes continuous limit. We are going to take from that.
so the speed is not fixed on the side, but it can.
Yeah, move around. That's the meaning of coherent states. So you have the sum of, a to the e to the I k1 and 1 plus k2 and 2. So this is e to the I k2 and 1 plus k1 and 2, and then n1 and n2. So this is the position of n1 and n2. And it's, so you can have a momentum, and then so the ratio between A and B is just you just call the n1 and n2 are opposite. So therefore, essentially, did I erase? Yeah, it seems that I erased. So the ratio between A and B is essentially n1 has a momentum k1, and 2 has a momentum k2. On the other hand, after the scattering, so you have opposite situation. K2 and K1 is swapped. So it has K2, and one particle has K2 momentum, and 2 particles have a K1 momentum. And the ratio between them is the amplitude, scattering amplitude. That's the picture. Any other questions? Yes.
You substitute this equation to this momentum equation, so where the second term on the right-hand side?
Second term, right-hand side will give rise to this n. Good question. Good question. Let me think. 2 over L. Good question. I see. Now I understand. So here, you sum over I is not equal to j, right? Sorry, I say it's hard to. My handwriting is horrible. So this is not equal to j. Not equal to j. So I is sum over. Here I is sum over, but here j is sum over, right? And if you use a relation between the terms, x is equal to minus terms x, minus x. If you use this relation, they cancel each other. Do you understand? So here I summation, sum is I, and here's j is sum. And if you sum everything, so you have to swap everything, right? And they cancel each other. So that what's left is what's important for momentum is this beta quantum number. Any other question? So I introduce this model to derive to get really some feeling of these, how to obtain scattering amplitude Hamiltonian and the energy exactly by hand indeed. So this is what Bethe has done in 1931. And we will move into the what Yang Qining has done in 1960. I already forgot the date. 67. So from here, not yet. So but the second half, we were going to move on to this 1967. It's a groundbreaking work by Qin Yan. So nowadays it's called Unbox Equation, or like a Gaussian model and so on, where you can solve the also exactly. You can determine energy and the momentum exactly, and the scattering amplitude exactly. Nowadays it's called exactly something. But before that, so we will see, as I mentioned, so we will take the continuous limit L goes to infinity and determine ground states. So, anyway, so ground states. So what are the ground states? So as you recall, so here we have a spin chain, and you have a minus sign in M side, and they are fermionic. So you cannot take the same. Each spin cannot take the same quantum number. So therefore, ground state, as you has to take each particle, each this magnum. So this spin down is called magnum. Each magnum should have a different quantum number. So as you recall, so here I introduced the Bethe quantum number, but here quantum number should be different for each magnum. So therefore, ground state should have, so you have a y1 to IM should take the following value. It depends on the M is even or odd. So suppose if it is odd, so you should have some 1 over M. Okay, 1 over M, whichever. And then next is minus 1 over M, minus M over 2 plus 1. Okay, plus 1. So it should have, the quantum number should have a different over 2 and dot M over 2. So at the end of the day, you should have M over 2 and then M over 2 minus 1. It should take the following value. Okay, do you understand? So so if you have a I, and it should be, so the ground state should be dense. Okay, but each magnum should have a different quantum number. So therefore, it should be like this way. M over 2, okay, so here is M over 2, and here is M over minus M over 2 plus 1, and so on. And you should go to M over 2, okay? Okay, so this, around here you have a 0. Around here you have a 0. And the excess state should have, it's not dense anymore, so there's a hole here. Okay, maybe I should write down the black dot or white dot, whatever you call it. So this is ground state. But to have excited states, you have a hole here. So it's like a Dirac hole. What you learn, hole here. There's an empty state here, and go to summer. So this guy goes to summer. Okay. So this is the excited states. Okay. That's, you can easily imagine what you get. Because I mean, as you can see, momentum P is a linear combination of the quantum number. And if I is very big, the momentum is bigger. Okay. So therefore, excited states, you have a lot of hole. So if you go to the excited states, you have a lot of hole, and this hole, this guy will go to somewhere else. And the momentum energy will become bigger. It's bigger. But in ground states, you have a different quantum number, but it has to be dense. it has to be occupied in the from minus m over 2 to m over 2. So that's what we expect. And we will take the limit, capital L goes to infinity from now on. Okay. So that's what we're going to do. And then to do that, so now we are going to take the limit L. So now we'll do discontinuous lattice or continuous limit. Continuous limit L goes to infinity. Infinity. So and then we will call it L. For large L, LDF is the number of quantum number. Okay, I think I should call it F. Okay, quantum number between in the interval F to F plus dF. Okay. F plus dF. And then Ki over what should I call it? Okay, maybe I should. And this lambda, so K and lambda are essentially the same. K and lambda is interchangeable. K and lambda is essentially the same. Interchangeable. So I already written many times. So lambda is equal to 1 over tanh K over 2. So, and then lambda j plus 1 minus lambda j has to be 1 over L rho. We just write down like this, like lambda j. 1 over L over rho, and the log lambda j, the meaning of is the number of lambdas in the interval between lambda and lambda plus the lambda. So in some sense, the density of momentum. Rho lambda is the density of log lambda, momentum between lambda plus dl. So the what we can just write down is f of lambda. Indeed, f I plus 1 minus f I is equal to capital I plus 1. So this is beta quantum number I over L. So let's see. F is the density of the quantum number I, and we know that the I is in a ground state essentially just next to each other. I plus I plus. Okay, I call it Ij maybe. Ij and the Ij plus 1 is just the difference is 1 in the ground state. So therefore you have 1 over L, which is equal to rho lambda j, and then lambda j plus 1 minus lambda j. Okay. So I just use this relation between this is the, you can treat rho lambda is the definition of given here. Therefore from here I can just derive that the FDF of the lambda should be equal to rho lambda. Essentially, the density of f is a density of quantum number I, and its derivative will give you the density of momentum lambda. That's what you get. So therefore, if you have observable in momentum space, So let me erase here. So if you have observable, whatever observable, if you want to take the expectation value of the observable in quantum mechanics, what we need to do is essentially we insert O lambda and then rho lambda, d lambda. So you introduce some cutoff minus q to q. So lambda is the essentially span from minus q to q. So essentially cut. It's up to normalization. Maybe you can just write down L. Okay. It's up to normalization. For instance, what we can do is that So for instance, the number of particle is indeed magnum is m, can be derived by minus q and q rho lambda d lambda. That's what you can. So if you just have the one in here, so you just count the number of magnums. So that's what you do. Okay. So now, so taking continuous limit, and unfortunately I have erased. So we want to solve this. We want to write down this 2L tangent inverse of lambda j is equal to 2 pi ij plus 2 times sum over j is I is not equal to j. Yeah, I is not equal to j, and tangent, so that's what we have derived last time, lambda j minus lambda I over 2. So that's what we have derived from the Bethe-Ansatz equation, and we just take the continuous limit. Question?
Is this operator O single trace operator or just general operator?
General operator, whatever operator. So if you want to take the expectation value, we just insert density and integrate over in momentum space. So general operator. Yep. And for instance, if you want to, if you want to find energy, so then this energy is essentially discrete space is ki squared is I is equal to 1 to n. That's what we already know from discrete space. But if you want to take a continuous limit, we just take the L minus q over q lambda squared rho lambda d lambda. That's a expectation value of Hamiltonian energy in continuous limit. Do you understand? So lambda squared is really operator now, energy operator. And the sum is become integral with density. Is it okay? Okay. And then now, so we want to write down this equation in continuous way. And this equation can be written continuous way is that, so just continuous limit tangent inverse of lambda of x, and we know density I becomes the f, so we already introduced, f is a quantum density of quantum number, so therefore you have the pi f of x and plus q minus q and the tangent inverse lambda of x minus lambda of, okay, maybe I should call lambda minus lambda prime over 2 and the lambda. So this is the equation in the continuous limit. Here, so we assume that the df d lambda becomes rho at the ground state. At the ground state, the ij plus 1 minus ij is equal to 1, right? So that's what I have explained from this picture. So therefore, this equation only holds for ground state or some very low excited states. This approximation is only valid for ground state and very low excited state. But if you go to the really high energy excited state, this approximation wouldn't be valid. Okay. Okay, so this is the continuous limit of this beta Unbox equation. And now we want to determine the energy and then in continuous limit. Okay, so we want to determine the continuous limit, and this continuous limit, one can do the following trick. So to determine this one, I mean, it's a bit ad hoc. One can just set Q goes to infinity first. So Q goes to infinity, this can be solved. Exactly by Fourier transformation. So this one was the mention. So this one is done by Fulton. So that's he noticed in the I don't know. I don't remember. Maybe you can search Wikipedia or whatever the internet. When was that? I don't. So this solution, exact solution, is called the Bethe-Fulton solution. But you can search in internet. I didn't do that. So, but you can do that. So by Fourier transformation, we introduce is as follows: minus infinity e to the I x omega c square plus x square dx is equal to pi over c e to the minus c. Okay. The omega. Okay, so then, so if you use if you do the Fourier transformation of this rho, where is that rho here? Rho tilde omega, and let's do the Fourier transformation. E to the I omega lambda rho lambda d lambda. Okay. D lambda, and do the Fourier transformation and plug this one into the how did it work? I already forgot. So let's see. So plug. So this one from here, what you should get is rho tilde of omega should be 1 plus e to the minus 2 omega is equal to e to the minus omega. Okay. So that's what you should get from this equation. From this equation. So let me think. I already forgot how to do that. Yeah, now I remember how to do this. Okay. Sorry, I think I missed something. This is. Sorry, I missed something. Sorry. So this. I'm sorry, I realized, but you have to insert density, low lambda prime. Sorry, you have to insert rho lambda. So as I mentioned, so always to sum over, you have to insert density of the lambda. Okay, to get this one first, take a derivative of this one. Take derivative with respect to so this with respect to x, log x. Yeah, with respect to lambda. Okay, sorry. Yeah, with respect to lambda. Sorry, I made a lot of mistake. So this should be lambda f. Yeah. So if you take the derivative of the dd lambda of this equation, it will give you the following. So from here you have a rho lambda. So if you take the derivative with respect to f df d lambda, you get the pi times rho lambda, and then this one should be derivative with respect to lambda will give you the following: q 2 over pi, I think 2 and 4 plus lambda minus lambda prime square rho lambda prime and d lambda prime. Okay, and from here you get 1 over 1 plus lambda square. So this is the derivative of this equation. Yeah, sorry, I think I made a mistake. If you take do you understand? So tangent inverse of lambda dd lambda should be equal to 1 over 1 plus lambda square. Okay. And if you use this relation, plug and take derivative, you get this. And now we can use the Fourier transformation for this equation. And you plug this equation into here, and then solve and use this relation of Fourier transformation. What you will get this one. Okay. And from here, one can just derive. So should I do that? Maybe I should do that. From left hand side, so as you can easily see, so from left hand side, if you plug this one into Fourier transformation, okay, so okay, so if you do the Fourier transformation e to the I x omega x lambda omega, and plug this equation, will give you log tilde omega 1 plus e to the minus 2 omega is equal to e to the omega. Can you see that? Can you see this equation if you do that? Can you see that? Or maybe I should write down more practically. I should write down this is equal to left hand side becomes e to the minus omega. So let's do the left hand side. Left hand side, you just do the Fourier transformation 1 over 1 plus lambda square e to the I x I lambda omega d lambda, and do the minus infinity to infinity. And then here c is equal to 1, so therefore you get the pi times e to the minus omega, right? So that's what you get. And from here, you have the just Fourier transformation. Oh, I think I made some conventional mistake, maybe. I think it should be plus, maybe plus. Yeah, to get the right formula. So you just get from here, you just get the rho tilde omega, right? Rho tilde omega. And then one has to do this integral. But this integral is also this Fourier transform of this guy. You can just use this formula. Okay. Do you understand? So let's do that in that case. So minus. I think I already take q goes to infinity limit. So therefore, infinity minus infinity 2 over 4 plus lambda minus lambda prime square. Sorry, rho lambda prime d lambda, and now we just do the following: infinity minus infinity, and then we just plug e to the I lambda omega d. What am I doing here? This is lambda prime and d lambda. Do you understand? Am I right on d lambda pi? And first you have to do the integral of d lambda. So just do the integral of this one. Okay? So you can apply this one, right? This formula. And what you get is I'm super lazy person, so I don't think I can. Okay. And this is equal to, I think up to factor, you should get the minus infinity e to the minus 2 omega. So now c is equal to, so you can just bring 2 out of the integral, I think 2. Yeah, 2. So now c is equal to 2. So you get the 2 here, and this 2 here cancel with this 2 here, right? And then you get the overall factor pi. Okay? Oh, misplaced. Okay. Okay. Do you understand? And then you get this one. And times rho lambda prime and then d lambda prime. But now, so when we do the integral of this one, you need to shift lambda goes to minus lambda prime. Okay? Lambda. So therefore, at the end of the day, so this one needs to be shifted. Lambda goes to minus lambda. At the end of the day, you get the e to the I omega lambda prime. Okay? So at the cost of the shifting. So therefore, if you do the integral of this one, what you get is rho tilde of omega e to the minus 2 omega. Do you understand? Then you get this one. And therefore, if you do the Fourier integral, so that's the how can notice. If you take q goes to infinity and then the Fourier integral, this can be solved exactly. And now we can determine rho tilde omega and plug back into here, then do the Fourier transformation. And one can determine rho. That's what Hausen noticed. Okay, so let's do that. So from here, rho tilde of omega should be e to the minus omega divided by 1 plus e to the minus 2 omega. And then do the Fourier transformation. Rho lambda is equal to minus infinity to infinity d omega over 2 pi, and then rho tilde of omega e to the minus I omega lambda. And this will give you, this is, plug this one into here, whatever. You can just ask Mathematica to do that, or whatever, whoever. Or you can just look at the book and you can have pi over lambda. So this integral can be done. So this can be done by exactly. Now we determine rho lambda here. Rho lambda here. And then we can plug this one into the original equation over there to determine the energy. So, for instance, one can just energy is indeed written as before, minus 2j sum over. So this discontinuous part is this one is 1 over lambda j squared plus 1 plus lj over 4. Okay. So that's the when the spin chain is discontinuous, and we want to take the continuous limit of this energy for magnum. Let me erase maybe. To take the continuous limit, and what we need to do is just do the integral minus 2L to JL and replace summation by integral by inserting rho lambda of lambda squared plus 1 d lambda and plus Lj over 4. And we know rho lambda already. We derived rho lambda. This is minus infinity to infinity. And plug this 1 over cos into over there and just do the integral. And then you can determine the ground state energy. That's okay. So let's do that. So this one is equal to minus J O L over pi minus infinity d omega plus e to the minus omega is just the cos over there. Just rewriting, and the minus infinity e to the minus lambda omega divided by 1 plus lambda squared d lambda, and then up to this factor, so plus Lj over 4. And now we can do the this integral exactly. You can ask Mathematica to do that. Essentially what you get is indeed this is, I mean, you can just perform this integral exactly minus Lj, and this is log of 2 plus Lj over 4. So this integral, I mean, one can just perform exactly, which will give you a log 2. And this is equal to minus 0.443 L times around minus 4. And this is the ground state energy. Of Heisenberg XXX spin chain in continuous limit. In continuous limit. L is very large. L is very large. And this is called Bethe Fulton exact solution. So this is the power of coordinate beta-Unbox equation. So if you assume just they're very simple. I mean, the Hamiltonian is given, and then if you assume the plane wave, how to say? So the wave function is the coherent state of plane wave, and then do solve the beta-Unbox equation by this integral. One can determine the ground state energy of the spin chain exactly in continuous limit. Okay, so let's take a break for 10 minutes break. I think it's a good place to stop. Yes.
I have a question. So, Heisenberg chain is the Heisenberg chain translation invariant? So, do we have another equation for that translation invariant?
What do you mean? I mean, if the system is translation invariant.
Yes. Also the wave function.
If system translation momentum is conserved.
I mean, should we have this equation?
No. What you mentioned is that the so e to the ikj product of j, right?
Yeah.
This is equal to e to the I k1 plus k2 plus ... km, right?
Yeah.
And we know the summation is conserved
Yes.
if it is translation invariant. Therefore, this is e to the I k total. Is it okay? in total. So therefore, this product is not one. It's some phases. Each is some power. I times some power. Did you answer the question?
And another is the reason I asked why this O operator O is general, because I think the spin change should represent like a single trace operator like this kind of operator, and this operator have the permutation invariance, which is a single trace. Yeah. So I think if you want to use that formula, the operator O should like the function of the single trace operator.
Why? But here, so operator O is infinity to minus infinity lambda, low lambda, and d lambda, and it should be function of the momentum.
And I think this should have like
this is momentum density.
yes. But the momentum density relates to the data answers.
Momentum density. Yes, that's true.
Yeah, but and the data answers correspond to the Heisenberg chain and its permutation invariant. So the operator.
I still don't understand this mean.
Means
What's x and y?
X, Y stand for some spin, like just like this, spin up, spin down.
But why it need to be
In
traced?
matrix form.
Well, I don't consider such a operator. I think you're talking about some different system.
No, I think this is the same.
But you're talking. I think I'm wondering. You're talking about ODN. I think this xy is the adjoint color of ODN equal to 4. ODN equal to 4 is related to spin chain. But in our system, we don't consider such an operator. We just have spin up and spin down and so on. So we don't have like a matrix form of operator.
And another question is that we're talking about the density of the state. Should we consider the degeneracy, like different combination of the rapidity of this lambda have different combination and they can still get the same energy?
No, because it's fermionic. It's fermionic. You cannot take the same step.
Did you do a Fourier transformation here?
Huh?
Did you do a Fourier transformation here?
Yeah, I think you need to do the Fourier transformation. And to get this one, you can use the Fourier transformation this one.
Yeah.
And then again, if you use, I think, somehow d omega 1 plus e to the minus 2 omega is equal to log n, log 2. If you do the Fourier transformation, you get this integral.
Okay. Yeah, but it's. So where is the I? Yeah, where is this term come from?
Oh, wait.
This came from Fourier
sorry. So this is I. Sorry, this is I.
可以填个普通的维道积分题，不是一个麻烦的维道。
算那个首先是3年函数跟2年函数，不是3年函数跟2年函数，一个叠加关系就是还多少我们计算题，你要把这个计算题单个系统这个整个不需要的。
It's for the homework you have.
Okay, so let's wait for a while for solution. Okay, maybe I should talk about this homework at the beginning. Another homework, sorry. Exam. Yes.
Where does this coming from?
No,
The system have 2 components.
no. So this is just a toy example. So this one we already considered before, like a previous lecture. We considered this Hamiltonian in the last lecture. But even here, when you solve this equation, this beta quantum number show up. This I, capital I. This will show up.
So they are different systems.
Different system, but you can solve it like a very similar way.
And we go to the same.
Yeah, we can do that. Yeah, we can do the same analysis.
And the result is different. The equation is different.
Yeah, equation is different. And also, yeah, beta and equation is slightly different. Yes.
I wonder, so this is the solution for the ground state?
Yeah. In continuous limit.
But I'm confused if the ground state is just the case of a line, all the strings align with each other.
Yeah.
So we don't have to solve it. We know its energy.
No, ground. Sorry. With magnum and magnum.
But why we don't have parameter m in this solution?
Because we take the q goes to infinity.
Oh, so
this q has information about m.
okay. So it means that m goes to the limit of 0.
Yeah.
Okay, I know. Thank you.
Good question. That's a good question actually. I should repeat. Yeah.
理论上垂直方向差2个地位，然后再用那个垂直方向，然后在这个这一堆地位和这2个地位之间有一个传输场，然后再把这个位给击掉，击掉之后我们可以得到一个这个分解的一个单有效作用量，这个有效作用量在3个point，然后又和就可以得到这个3个分解函数的地位，或者是
这个里面用到的技术太多了。
Good. I thought he will ask me why I teach this one, this in particle physics, but he didn't. I'm glad. I'm glad. He has left.
那2个人讲。
你不行。
你们有资料吗？
应该是自导自演，上次没有点。哎，你这跟我看的一样啊！你是这个 acting 几年？这个吗？当时他在看个全量做的太强，做的是 front， 是 front， 有趣。然后又比较麻烦，就是他写个新的故事类，他写的他的小在转换中并不擅长，比 spin 更融入，它是一个那种分析的创作。然后
讲自己工作吧。
没有，他是现做的，然后他找了一个新的老师来，
对，他就相当于做这个工作，然后把它变成小的台，
然后又发表了，就是在推出的
台，切入发
这个发那反
Okay, shall we resume? So, couple students did submit the homework, last homework. So I will wait one more week for sending solution. So if you want to solve the last homework, and of course it's a difficult one. The first problem is the straightforward calculation, but the second and third one is a bit difficult one, case equation and then queried algebra. And those are difficult one. I mean, if you want to submit from now, it's totally fine. I'll wait sending solution for one more week. And then exam. Unfortunately, I had to do exam. I don't want to do the exam, but unfortunately, school demands me to do that. It's mandatory, so unfortunately, you have to do that. As I mentioned, homework score almost determined your final grade, 80%. And then 20% is exam. And then final exam, you can Kaijuan. It's open book, whatever. So you can bring whatever book you want. Yeah, it's okay. I mean, but essentially, if you print out my but I don't want. Okay, I mean, whatever method you can bring iPad and so on, whatever, but just don't connect to internet. Don't connect to internet. I mean, I just don't want to do the final exam, but I have to do. But yeah, just do not connect to internet, but then you can use iPad and so on to see the book. Yeah. Anyway, so you guys already did lots of homework, so but just don't lose your don't waste your effort by connecting internet during the exam. So then open book, and then what are the content? I already created final exam. What are the? Let me check now. What are the content? I already forgot what are the final exam. Yeah, essentially, yeah. I mean, you need to be familiar with OP computation or like whatever computation ratio, bilateral algebra and so on. And then yeah, just review minimal model, West-Zumino with the model, like that. That's enough for minimal model, West-Zumino with the model. That's enough. Yeah, just familiarize yourself OP computation and then computation ratio, bilateral algebra and so on, and then physically just review minimum model. I think that's it. Okay, so that's yeah, the plan of final exam. Do you have a question about the final exam? Any other question about any other question apart from even?
Can we use mathematics?
No. If you want, but I wouldn't. Unless you're super good at coding Mathematica, it wouldn't help. Yeah, it wouldn't help. Okay, to be fair, so let's not allow to use the Mathematica. I think do by hand in the computation by hand. Any other question? Not only the
exam more difficult than the homework?
Of course, easier.
Much easier?
Much easier. Okay, so usually homework contain like kind of straightforward computation, right? Like a derived equation and so on, or like a derived homework always contain this level. But I wouldn't say much easier. Some problems are very easy. Some problem. Yeah. So anyway, students so as you know, my course is already very difficult, and we go very farther. Some students already complain to me it's too fast and so on. Yeah. Anyway. But yeah, at least we cover basic stuff of CFT, so you learn a lot. So just I mean, if you solve the homework, I think you can solve final exam if you spend enough time, but anyway, so the time is limited, like 2.5 hours or so. This, yeah. Okay. Yeah, about grade, I may try to negotiate this stupid rule by Fudan. 30%, only 30% of students can get a grade A and so on. I may negotiate with Fudan whether I can change this one, because otherwise, at current situation, it's a bit unfair. So otherwise, but anyway, so grade is great. So don't worry.
It also says if the student, the number of students is less than 10, they will, the grading is not constructed to 30%.
Oh, there is such a rule? Oh, okay.
Still need to negotiate with the
Fudan. Okay, I will do that. Yeah. Okay, anyway. Yeah. Okay, I will do that at Fudan. That's about grade. Okay, let me go back to the contents. There is a good question by him. So he asked me the following question: ground state. So ground state can be always like a spin always up. Is it? So why do we need to do this kind of computation? That's his question. Here we already introduce m magnum, and then m goes to infinity. M magnum, and m is related to this cut. Already erased. It used to be Q. Q and m is related. How many magnum you have? And in fact, Q goes to A goes to infinity, and Q goes to infinity corresponds to. Actually, you can solve this plug. I already erased. It corresponds to m is equal to L over 2. The half of the spin is up, and the other half is spin down. Spin down. And so the ground state here, it really corresponds to this guy. This guy. M is equal to L over 2. And in total, a spin becomes, here it's the spin is all up, so the spin is the L times 1/2, right? L times 1/2. But in this case, spin is really, the spin is 0. If you solve this continuous limit of the Heisenberg spin chain, L goes to infinity, Q goes to infinity, you can actually verify M is equal to L over 2. So half of spin is up, half is down. And then we can just solve the equation. And this is the meaning of ground state. So to get this, of course, this configuration, you sometimes need some very weak magnetic field to spin aligned to up or down. But in this case, if there is no magnetic field, you can have also this state as a very low energy. So that's the concept. Okay. Should I talk about first 6 states or go to Unbox, whichever you want? So this is ground state, and maybe we can talk about first excited states, then I cannot reach to the Unbox today. Whichever. Which do you think is appropriate? Maybe I can talk about the Unbox, maybe, instead of first excited states. Okay. Let's do that. You will erase the blackboard. Oh, and also, so somebody mentioned there's an I missing here. Here it should be e to the minus. If you take a note, it should be e to the minus I. So I missed the I. Okay. Now let's talk about Unbox. Yeah, I start writing a lecture note, but there are still lots of typo and so on. Maybe before the exam I will create a lecture note for integral system. But anyway, I'm too busy to do that. But yeah, maybe during final exam I will type. Maybe I will include first excited states in the lecture notes so that if you're interested, you can read. Where was I? Good. So last time, we talked about Hamiltonian with the delta function potential. Oh, by the way, so this is called quantum many-body system, actually. Most of people, many-body system. System. And Bailey has introduced this quantum many-body system. And then to see delta sum over so delta function potential and C is reversible. C is positive, so therefore it becomes reversible. And then so here, so last time we talked about the n, so the n bosonic. So last time n bosonic particle, and we solved we derived the Bethe-Ansatz equation. So Bethe-Ansatz equation for delta function. Now we change to bosonic to fermionic. Spin 1/2 particle. So bosonic, you cannot distinguish the particle. Okay? You can have the same states. So, but the spin 1/2, if it is fermionic, this you cannot have the same states. The different particle, different fermion cannot have the same state. That will give you the difference. And also, you have again. We will use the coordinate Bethe-Ansatz equation. Coordinate Bethe-Ansatz equation I already erased, but the sum of whatever a q1, a qn, m, e to I already explained many times. x1 plus k q2 x2. So this is the wave function you will have. But in addition to wave function, you have. So this is the spatial one. Spatial wave function, but the total wave function is indeed spatial times the spin. You have a spin up and down. So therefore, you have whatever plus, whatever plus minus or some linear combination of this, some linear combination of whatever plus some number and state. Plus minus whatever, or minus. So you have an internal degrees of freedom. Okay. So that's the difference between bosonic and fermionic. That will make a much richer from moving from bosonic. So this one, bosonic is done by Bethe in 1931, but this spin 1/2 is done by Yang, the most famous physicist in China, I think. 1967. So this was, it took 36 years to solve. Move from bosonic to fermionic, spin 1/2. So that's what we are going to see. Okay, that's what we are going to see. So let's do step by step. So I don't want to go suddenly to n. So again, we just consider n is equal to 2 case. N equal to 2 case spin 1/2 particle equal to particles. And again, I use the following: A1 is equal to Aij by sorry, not 1, 2. I call it 1, 2. 1 x1 plus k2 x2 plus a21 where x1 again in the risk region. So again, 1 is this region, and then 2 is e to the I k1 x, sorry, k2 k1 x2 1 to 1 e to the I k1 x1 plus k2 x2. Okay, so this is the beta ansatz, coordinate beta ansatz again, I will assume. Ansatz. And again, we will do the following the. So here, so we are interested in just look at the x1, almost x2 around the region x2, and then do the integral of this Hamiltonian, and what you get is the Hamiltonian integral around of Hamiltonian around x1 is equal to x2. Okay, and then as I mentioned many times, you get that this one x1 is equal to x2 plus 0 minus sorry, I think maybe I should put the psi here. Psi. So a Schrödinger equation is equal to 2c psi. Okay, so far it's the same as bosonic case. For bosonic case, we immediately identify this guy and that guy and so on. But the fermionic case, this is not the case. So we will see step by step for fermions. Okay, step by fermions. And if you plug this coordinate beta ansatz equation plug here, then what you get is the following: 2, 1, region 1, and A1 2, 1, region 2 is indeed equal to 1 over k1 minus k2 plus IC minus IC, and the k1 k2, k1 minus k2 minus IC divided by multiplied by A1 2 I A1 2. So this is the what you get from plug this coordinate beta ansatz into this Schrödinger equation. Okay. Of course, you can just you have to use the following. So you have to use also this one, x2 minus x1. I mean, you can just swap x2 and x1. Psi and the x2 is equal to x1 plus 0 and dot dot dot. So if you use this two Schrödinger equation, you get and plug this one into here, you get this one. And now, so we need to take care of the internal states. So we need to be careful about this one. So now it's a spin 1/2. So therefore, if you have a spin 1/2, so this is okay. So in the homework you already solved, right? It's trivial in SU2. Okay, this is already you did in the homework. So this is what is the dimension of this one? Huh? 3. So it's called triplets of sometimes, and this is the dimension is 1. Okay, and the base is plus plus, plus minus, plus minus plus, and then minus minus. On the other hand, here is the base is plus minus 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 plus. Okay, so this is the basis. So therefore, here if you swap two particle to internal state is just a stay as it is. Okay, stay as it is. On the other hand, here if you swap internal degrees of freedom, you have a minus sign. Okay, minus sign. So therefore, so there is a difference between a triplet and then singlet in the internal states. But so that affects the coordinate wave function. In fact, if you swap the two fermion, total wave function should get minus sign. Okay, otherwise that Pauli exclusion principle. So total should get the minus sign if you swap two fermions. So therefore, so A. One, two, region 1 and A21, 1, 2, A21, sorry, A21 region 1, and then A1, 2 region 2. If you swap these two, oh, I'm sorry, I didn't write down. So region 2 is of course x2, x1. X2, X1. So if we swap this one, so you get the region 2, if you go to region 2. But now, so there is a difference between plus minus sign. So this one, plus sign is singlet. Case. And minus sign is correspond to triplet. Do you understand? So here, internal, if you swap the two particle, internal state doesn't give a sign. So therefore, the coordinate should give you, coordinate wave function should give you minus sign. On the other hand, here, internal state will give you minus sign. So therefore, the coordinate wave function should be plus, even if you swap. So there is a difference between a singlet and then triplet in the wave function. Undergraduate students looks very exhausted due to coursework, I guess. And application, I guess. Okay. Okay, so then, so if you take it in this account, and then we introduce the following notation. C12 is equal to A12, 1, okay, maybe Aij, Ij, 2. And then Aij. So this equation, okay, maybe star. So this star can be written as the C Ji is equal to Y Ij C Cij. Where the Cij also depends on momentum K so K1 and K2. It depends on K1. So this Ij matrix can be understood as this matrix. Okay, this matrix. And then if you yes.
Should be A1, 2.
Where are you pointing out?
You have both left and right hand side have A2, 1.
A2, 1.
I mean, the first one.
Which one? Here?
The star one.
This is star one.
Is that
A1, 2, change. Thank you very much. Yeah. Thank you very much. Thank you very much. You're right. Yeah, thank you. Okay, so that's right down, and it taking care of this sign issue. Then what you get is this Aij, and then K1 and K2 can be written as follows: K1 minus K2 P tilde minus by C over K1 minus K2 plus I by C. Sorry, I think I shouldn't write down like this way. Okay, let me reformulate. Okay, I think I shouldn't write down like this way, K1, K2. I think I should call alpha and beta. And this is 1, 2. Okay, maybe I should call, okay. Maybe I should call 2, 1. And then 1, 2, 1, 2, 1, 2. And 1, 2, 1, 2. So this P tilde 1, 2 acts on singlet is on 1 or minus 1, or this is for singlet, and this is triplet. So do you understand what I mean? So it used to be, so in bosonic case we use this plus sign. Bosonic case, we identify A12 and A12 in the region 1 and region 2 because it's, you can just, in bosonic case, the interchanging of the two bosonic particles doesn't matter. So therefore, you can identify these two. So bosonic case, we use plus sign. And then the beta under the equation is really, here is actually indeed plus. It should be plus sign. It used to be plus sign, right? So as you recall, maybe beta under the equation bosonic case is minus IC over K1 minus K2 plus IC. So this is what's bosonic case. However, if you use this the boundary condition, whatever, A12, region 1 and region 2 are connected by minus sign. In fact, if you solve this equation, you get the minus sign here. Minus sign. So therefore, depending on the region, depending on internal state, the beta under the equation will be modified. So from here it's hard to see, but I will explain why this is the case. So let's look at the singular case. The singular case and the singular case. So you just have A. So A12 of 1 is equal to A12 is of 2, and the A21 or region 1 is equal to A21 region 2. And if you take a ratio A21 and 1, and then A1 to 1 is indeed equal to K1 minus K2 minus IC over K1 minus K2 plus IC. Okay. So this is singular case. But the triple case, you can have A12 of I is equal to A21 is equal to 2. Or maybe I should, yeah, A21 A12 minus A12 of 1, and then A21 of 1 is equal to minus A21 of 1. And if you plug this one into here and solve the coordinate invariant equation, indeed everything is the same. Everything becomes same. Moreover, if you plug this minus sign over here, and what you get is indeed K1 minus K2 minus sign minus IC over K1 minus K2 plus IC. Okay, IC. That's what you get. And as you can easily see, this is just trivial. It's just minus 1. Can you see that? It's just minus 1. So it's a trivial equation. So therefore, all the coefficients can be identified.
I think that should be 2.
Huh?
Right-hand side. A1 to 1 plus 1.
Oh, thank you very much. Thank you very much. So everything is trivial. So therefore, the difference between the triplet and singlet is very significant. And so
that means A1 to 1 is 0.
A1, 2 is equal to 0. I see. It should be, let's see. Is it correct or not? It becomes just spinless. Sorry, I got confused. It should be 0. But if you solve, huh?
Only A21 goes to A21 and minus.
And that should be A1 to 1 plus minus A1 to
You have read this formula on the above.
This one?
Yes.
Yeah.
It's
It's different from this one.
It's different from this one.
because
The right-hand side
Right-hand
should
side should
be
be minus
the
A1.
bracket number is right.
Oh yeah, you're right. So it should be, sorry, this should be 2 and then, sorry. Yeah. Are you satisfied? Okay, thank you very much. Yeah. So this is a case. So therefore, in the if you introduce the spin 1/2, so the depending on internal region, so the coordinate beta under the equation becomes non-trivial and it becomes this trivial. And that is of course the case when you increase the number of particles. So now, so we just introduce again n particle and spin 1/2 fragments. And then, of course, with delta function potential, delta function potentials. And now, so we can again assume the coordinate beta unders. Maybe n e to the I k1 kq1, and q is the symmetric group x1 plus k q2 x2 plus plus k qn xn, and this is a region for x1 x region. So we assume this is again a coordinate beta ansatz. But we need to take into account also internal degrees of freedom. So internal degrees of freedom is the you need to take into account, and also region can be changed. So therefore, you can just have the so this region, and then if you go to the sums, if you swap the indices here, xp1 xpn, then here I think you just call it the 1 n, but here you just need to have psi a p1 pn, and also q1 qn, and then you have e to the I sum of x qi and then k to the qi and x to the pi. Okay. That's what we need to do for the I think I should change the notation actually. I think my note is different from different notation. Sorry. Let me change the notation. It's better not to mistake. Let me change notation. I call it this is P. Sorry. I call it P. This is P. Sorry. So this is Q. Sorry, I changed the notation. Sorry. P, and then this is P and then Q, and this is Q, and then Q. Sorry. So region. Okay, so this is the coordinate, and then this is the sum over P on Sn. Okay, so this, and now see again. So we again introduce the following notation. So this A P1 dot Pn and Q1 dot Qn is indeed n factorial and then times n factorial matrix. So because the permutation group, the order of permutation group is n factorial. So P has the choice of n factorial, Q has a choice of n factorial. Okay. Okay, and then we can just so we can just consider this one is the C P. How to say? So n by n matrix. So you can have the. So how to say? It's very difficult to explain, but what I meant is that the how should I write down n factorial matrix? So here you just have the C P 1 and C P2 and dot C P n factorial. So you just consider this column vector of this can be, so you just write down this n by n factorial vector as the really column vector where Pi is a choice of this permutation group. Okay? Permutation group. And then, so what we have introduced last time is the indeed, so we just introduced the, for two particle, we just have Cji is equal to Yij and alpha beta Cij. So, and we introduce this matrix as the Ki minus Kj times P tilde alpha beta minus C divided by Ki minus Kj plus Ic. So here, this Ij plays the role of P. So this Ij here plays the role of the choice of P. This corresponds to the choice of P, and indeed alpha beta indeed corresponding choice of Q. Choice of Q. So here, P tilde alpha beta is the when you swap the alpha beta particle. So here, what I meant is the it's hard to explain. It's very difficult to explain. I and J, so okay, alpha particle and the beta particle and the Ki and the Kj, and they just this Y factor really come from Ij schematically. Beta is really come from Ki, alpha particle, and then Kj. And then this coming from Ki and the beta particle. And that's how it works. So now, we will do the same thing for this column vector. So this column vector, it used to be A12. It used to be A12 and A21 region. A12, region 1 and region 2. Okay. So you just fix the fix a P and change the Q. So that's you get the column vector. Fix a P and change the Q, and that will give you column vector. And then if you try to change the P by permutation, then what you get is P prime is given by related by P by this matrix P, Ij, and alpha beta. So here, what we have is the essentially P1 dot Pj. Where is not good. So and then Pj and then Pn, and then here I think so. We assume that the Pi and the Pj is what I'm doing here. Sorry, I got confused. Sorry. I think I should write I and I plus 1 in that case. I and I plus 1 and I plus 1, and then we just swap between these two. You just need to swap between these two and to get the P prime. So this is P, and the P prime is just you just swap I plus 1 and I. So that's P prime, and the vector column vector is related by this matrix Y. And then if you try to solve, so this Y vector matrix Y can be just obtained by solving this by plug this coordinate beta ansatz to the Schrödinger equation. And in fact, in order for this coordinate beta ansatz works, what we need to impose is the following condition. This matrix is equal to this matrix, and I just call it I and J, and then L, and I, J, and L, and insert this one. Y matrix. So here you insert Yij alpha beta, and here you need to insert Y. I think is it big enough? I hope it's big enough. I think I should write it bigger maybe. Anyway, so if you write down this one, it's over to the gamma. JL, and here you have assigned Y, beta, gamma. I think I should use the color chalk. That makes it easier to read for you guys. Y, I, J, alpha, beta, Y, beta, gamma, I, L, and then here Y, J, L, alpha, beta, J, L, and here is also Y, beta, gamma, I, J, J, L, and then here Y, I, L, alpha, beta, Y, I, J, beta, gamma. So yeah, so here, so you have the so alpha particle and beta particle, alpha particle, and then here is gamma particle. And if you have a cross, if you take, when they cross them together, you assign this Y function, Y matrix, and so on. So in order for this coordinate beta ansatz equation works, so what Yang has found is that the alpha beta JL Y I L beta gamma and then Y I J alpha beta should be equal to Y I J beta gamma Y alpha beta I L Y beta gamma JL. this relation needs to be so this matrix Y needs to obey this rule. So this is called Unbox Equation. So since now you have the different, so this Unbox equation involves this matrix. This is K I J. Oh, I have written here. So this P alpha beta is really depends on the either singlet or triplet. So this becomes matrix now. Okay, so it becomes matrix. So it's a matrix value. So it's no longer the scalar value. Okay, so therefore this matrix needs to obey this condition to solve the spectrum exactly. So that's this coordinate beta Unbox equation needs to obey. And moreover, I think I should erase here. I think I just introduce this matrix body. And if you want to do the same game as before, so what I meant is that if you have the n particle and you want to bring j particle like this way, and find e to the ikj L is equal to product of some scattering amplitude. So what we need to do is essentially 1, 2, 3, 4 and j particle, and at the end of the day you have L particle, L's particle, and here what we need to do is indeed yeah, so here the particle alpha is scattered alpha. So therefore here if you only assign this y here, so if you only assign y here, so j's particle becomes, I mean the particle is now swapped. This becomes j and this becomes 4. This can become 4. So therefore, to do the same game in the bosonic case, in addition to the this matrix Y, you need to swap the particle. So you need to swap the particle. So therefore, the scattering matrix S is not the same as Y over there. What you need to do is Sij is indeed equal to P tilde Ij times Y Ij and Ij. Here P tilde is the operation. So this is the operation. You swap to swap coordinate alpha and coordinate beta, x alpha and x beta, xi and xj. So you need to introduce this one. So therefore, if you multiply this one, so they plug this one into here, what you get is ki minus kj minus ic p tilde ij divided by ki minus kj plus ic. So in addition to this matrix Y, so if you assign matrix Y, I mean the j's particle is really goes to the upwards, and then the i's particle goes to the left. So you have to change the matrix. So you need to introduce p tilde and plug that one into here. And in fact, so the alpha beta. So now alpha beta becomes ij, and the p tilde ij is just a swapping operator square is equal to 1. So then you get this one. And now Bertrand's equation becomes the e to the so e to the e here. So now we can use here. Bertrand's equation becomes S I j I is not equal to j. So since now it becomes matrix value, so this is now matrix value. So this Bertrand's equation is very hard to solve. So this is called generalized, yes, according to Jan, Bertrand's equation. And then we want to solve this generalized Bertrand's equation by using Unbox Equation. And then unfortunately I don't have a time to solve at this moment. I think it takes one more lecture to solve this Bertrand's equation. Okay, so it's a bit early, so let's stop here today. Yeah, I will explain a bit more detail. So my preparation for Unbox is not so good today, so let's stop here. So any question? Any other question?